let's practice where we left off. We left off here. We should be pretty comfortable with naming something that looks like this. And I'll just do something fun. If I did something like this to you, you should be able to say, oh, okay, I could name that. Looks like a bunch of lines on the whiteboard. No, it's not. It's actually an alkane. So let's identify the longest chain. So you got a lot of them. 1, 2, 3, 4, 5. Nope. 1, 2, 3, 4, 5, 6. Nope. 1, 2, 3. Probably not. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Probably 8, right? So if I circle the 8, all of those in the blue are named how? One word. How? Octane. Okay, so all of those are named by saying octane. Rule number 2, I think we did in green. And that is to circle, number, and list all of your functional groups. So I have to decide what side do I start numbering from. I have a 1, 2, 3, 4, or I have a 1, 2. So obviously I'm going to number from 1, 2, 3, 4, 5, 6, 7, 8, which confirms octane. At 2, I have a methyl group. At 4, I have a methyl group. And at 5, I have an ethyl group. We all good so far? Okay. I can track these down because there's 2 of them. So this becomes 2,4-dimethyl. Okay. And now I bring them together through the Germanic method of one word or using dashes and commas to bring it all together. Now, in the alphabetization rule, it is alphabetized by the original, not the D. Okay, that's just one of those little nuances that you'll get stung with. It's just the way that the IUPAC conference that meets in Sweden every 2 years to go over new organic molecules and how we're going to name them. So we alphabetize off the M because it's the parent, not the D. The D is the descriptor of the parent. Okay, so that's just one of those little rules with one exception. ISO. I always have to have an exception, right? ISO does actually become part of the word, so they put I as the alphabetical correct one. I'll talk about that a little bit. Okay. So putting this all together, then E comes before M. So it's going to be 5-ethyl dash 2,4 dash dimethyl octane. Okay. And that's where we left off on Monday, right? Good? Good. Okay. So 2 things that we need to add to this before we move on into alkenes, and that is what happens if I have a halogen on one of these things? What happens if I have something that looks like this? Okay. So halogens on molecules, and there's quite a few of them because there's a lot of the neoplastics and the not necessarily anti-inflammatories, but a lot of anti-neoplastics have the halogens on, fluorines on, chlorines on, bromines. So remember that fluorine, chlorine, bromine, and iodine. So sitting over here, these all form one bond, right? Just like hydrogen. So they're named just like a branch, but instead of it being a fluorine, and fluorine. Remember, fluorine has a U in it. Okay, it's not FLO, it's FLU, fluorine. We lose the INE and we put an O. That's all we do. Chlorine. We lose the INE and we put an O. Bromine. Again. So it becomes fluoro, chloro, brom-O, and it's alphabetized by whatever the halogen is. So in this case, again, my rules say circle the longest chain, number it. In this case, I'm not going to get into which order it is, but it's the fluorine because it has a higher molecular weight. It's called the Kahn-Engel-Prelog rules. They're really gory, and that's for sophomore level organic, not for this level organic. But fluorine does have a higher molecular weight at 19.0 and carbon 12.01, so it has a higher priority. That's just one of the rules. Again, that's a sub-rule that I'm not going to hold us accountable to, but I'll just use that. So in this case then, I'm going to have butane. All right, I'm going to have a 2-fluoro. I'm going to have a 3-methyl. Since F comes before M, this is going to be 2-fluoro dash 3-methyl butane. Okay, isn't that cool? It's pretty cool. Pretty straightforward again, very systematic. Follow those 3 rules. It's not that difficult. Okay, we're going to build on those rules. It's going to get more difficult, but for now, that's what we need to know. Okay, any questions before we move on? That's the fluorine. So we just added the fluoro. Again, they're treated just as alkyls, just alphabetize them and put an O at the end, right? Okay, oftentimes in chemistry, in organic chemistry, we have rings. In fact, if you look at a molecule that we will see down the road, especially when we get into the lipids, this molecule is a very special, molecule. You know what it is. You might not know the structure, but you know the molecule. You've heard of the molecule because it has a bad, it gets a bad rap, and it should. It's actually a great molecule. We need it. We'd be dead without it. Okay. So that molecule right there is called cholesterol. You ever heard of cholesterol? Okay. Cholesterol is a very important molecule. When we get to lipids, you're going to see why it's important. If you don't have enough cholesterol, you die. If you have too much cholesterol, you're going to die. So it has to have this perfect balance because of the way it's a lipid. It sits in the lipid bilayer. Some of you have heard about the lipid bilayer, maybe in a biology class. Some of you have seen this little cheesy cartoon that's oftentimes in your textbook that looks like this. In this class, we're going to understand why that is, and it aligns itself into this magical bilayer. We have this greasy nonpolar, and we have polar, so this is a lipid bilayer, okay? With that, with the lipid bilayer, we have to have rigidity with that, okay? So this layer literally is like, it's like water. It's like a sea, probably a little bit thicker than, a little more viscous than water, but like a oil, it'd be like oil, and it's very floppy. How do you make it non-floppy? Well, you stick this in here. So that thing sticks its little OH right here, puts its first ring here, and its big greasy tail there. So it sticks it in there, and then we put another layer here. It might have one here, right here, and then it might stick one down here. OH, bump, 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 greasy tail, okay, and bump, bump. And so you stick this greasy molecule, this rigid molecule. This molecule is fused, it's locked. It's really rigid, it's like a brick. So you put that in with this floppy sea of lipidness, and it gives it rigidity. So you have to have a level of rigidity for the cell wall in order for it to maintain its structure. If you get too much cholesterol, it gets too rigid, okay? That leads to disease. If you don't have enough cholesterol, it's too floppy. That leads to badness and leaking. So you have to have that perfect balance of cholesterol, and that's why the HDL, the LDL, and VHEDL, or whatever they all are, you're going to learn those much better in your biology classes or your nursing classes than you will in this, but we'll talk about the chemistry of it, okay? So, back to the ranch. Cholesterol has a 6-membered ring. 6-membered ring, 6-membered ring, 5-membered ring. So, alkanes like to form rings, and in fact, these aren't the only ones that we're going to see. If I take and remove that and remove this, check this out. If I make that, okay, that's testosterone. All right, you can make progesterone. Progesterone is that. All right, estrogen is that. So you can see that all of these compounds that work within our body in a very important way have these rings in them, and they're very important. So this is why it's important that we understand these rings. We'll get to the benzene ring on Monday. It's very important as well. So that said, if you look at these alkanes, I can make an alkane of 3, very strange, but I can do it. I can make an alkane of 4, which, by the way, which is basically penicillin. penicillin's a miracle drug. We'll talk about that. It actually has a 4-membered really string, what's called beta-lactam in it. We'll get to that when we get to nitrogen chemistry. 5, you saw a 5 up here on cholesterol and the other steroids. 6, okay, and 7, 8, 9. 7 and 8 are not as common. Your most common by far. 6 is your most common. It's the most stable. That's why most molecules have that in them. And 5, and even some of the cool things. I mean, if you look at a molecule, go too fast here. If you look at a molecule that looks like this, okay, all right, it's eucalyptus. Beautiful aroma of eucalyptus. You might look at a molecule that looks like this. Okay, that's alpha pine. Oops, sorry, that's not. It's alpha pinene. All right, if you've ever smelled pine needles or pine saw, that real pungent odor, you see all of these alkanes. This is an alkene. This is a ketone. But you see these rings in them. There's a 6-membered ring here. There's a 6-membered ring there. There's a 6-membered ring here. There's a 4-membered ring and a 7-membered ring here. And you see these rings within all these natural products, so they become important to us. All right? This is going to be a real simple name, and you can see that this one here is propane, because it's 3, but we put a cyclo out front. So it becomes cyclopropane. Now, cyclo becomes part of the word. So it's alphabetized off of the C. Okay, so we're not going to get into the rules, but this is cyclobutane. What do you think this one's going to be called? Cyclopentane. Yeah, cyclopentane and cyclohexane. Okay, so those are the cyclo series. All right. And in nomenclature, if you have a ring in the molecule, the tie goes to the ring. So meaning, if you have a molecule that has both a ring and a big long chain on it, the tie goes to the ring. If the chain is longer than the ring or more carbons in the ring, then the chain, the branch or the longest chain gets it. So I'll give you just 2 examples. So if I have something that looks like this, okay, the cyclohexane is the base name. So we would circle that just like we did with our other rules. Okay, so that becomes cyclohexane. And then when we circle that, we're going to have 1, 2, 3. So it's going to be a 1-methyl, 3-methyl. So it's going to become a 1,3-dimethyl cyclohexane. Okay? So that's the way they're named. And the rule of thumb on these is to number them in the order that gives the branching the lowest numbers possible. Okay? So, for example, if I give you something like this, there's really several ways to number that. Okay, I could do 1, 2, 3, 4, 5. 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 Which one gives the branching the lowest number possible? Well, it's going to be 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Does that make sense? So this is going to be 1, 2, and 3. So that's going to be 1, 2, 3 trimethyl cyclopentane. Okay? Good? Good. Does that make sense? Any questions on that? Should we practice one, just for fun? All right, let's do it. So this is really trying both new things that we've learned today. Seven-member rings. You look how bad that is. Seven-member rings. They are so hard, I think, because they're not symmetrical.
Well, like some of the things don't even look like theirs.
Don't even look like a mouth here. Okay, let's try this one. So again, it should be a seven-member ring if I did it right. It doesn't looks awful. 1, 2, 3, 4, 5, 6, 7. Yeah. So cycloheptane should be our base name. Okay, so let's figure out how to number this thing. I could do 1, 2, 3, 4, or I could do 1, 2, 3, 4. Which one's lower? Here's a way to do this. Watch. 1, 2, 3, 4. So I have a 1, 3, 4, which equals 8, right? I have a 1, 2, 3, 4. So I have a 1, 2, 4, which equals 7. Which one's a lower number? The green one. Okay? You see how that works? So that gives it a lower number. And it makes sense, right? Because a 1, 2 is lower than a 1, 3.
Okay.
Right? So I'm a 1, 2, 4, or I'm a 1, 3, 4. What's lower, 2 or 3? 2. So it's 1, 2, 4. Okay? So again, you can go through the rules. I guess I can keep consistent with our rules. So I'm going to have a branch here, a branch here, and a branch here. My green's dying. So I'm going to have I'll just go ahead and do 1,4-dimethyl. I have a 2-fluoro. Okay, so I alphabetize by the M, not the D. So this is going to become 2-fluoro dash 1,4-dimethyl cycloheptane. Okay, that brings in what we learned on Monday and the two new things that we learned today: naming halogens and naming rings. The one nuance that I talked about with rings is if you do have a branch that is longer than the ring, the tie goes to the ring. If the ring, or if the branch has more than the ring, something like that, all right, something like that is going to become, again, which one of these is the longest ring, or which one of these is the longest chain. The longest chain is going to be 1, 2, 3, 4, 5, not 1, 2, 3, 4. So it's going to be, that is my longest chain. Therefore, it's going to be a 1 cyclo-bu, not tane, but butyl pentane. Okay? Yes?
Why is it butyl?
Oh. Cyclobutyl, 1, 2, 3, 4, cyclobutane? If that's just,
Why
if
is
that's
it
just,
out?
what's that? Oh, because it's a branch. Methyl, ethyl, propyl, cyclobutyl, butyl, pentyl. You just put a YL on it. Yeah, good. Good. I like the questions. I like when people respond. Okay, if you're tied, tie goes to the ring. So that's going to be propyl, cyclopropane. Does that make sense? It's kind of quiet in here. Is that because it's Friday, or is that because the Rams are going to win on Sunday? Both? No. So, those of you that watched the Flat Earth Round Earth, did your homework for Wednesday, did anybody notice something interesting about that 14-minute documentary?
I just wanted to say, of course, it took place in California.
Of course.
Yep.
And there's a longer version, it's like an hour and 20 minutes, which is better. I just couldn't figure out how to get it to an M24 format. It only streams on Netflix, and it's actually very well done, but that was like a 14-minute version of a very similar documentary. What were some of your thoughts on that? Yeah.
Why the heck, in God's green earth, would anyone hold to flat earth in today's day and age? It makes no sense.
California. It's like 6.5 million people live in it. Yep. Well, okay, so then that's the thing I asked that question of, did either of them change their hypothesis based on the data? It's like, no, well, the round earthers didn't need to because it confirmed their data. The flat earthers were like, well, no, it's just because it's refraction coming off the water, right? So they rationalize it away. And did anybody pick up the extra scientific bias from the flat earthers? Did anybody pick it up?
They were basically saying that it's some kind of shadow government that you can't detect.
Yes.
It's been there forever.
But
for no reason.
that's their conspiracy belief. But what was the extra scientific information that they relied on more than the scientific information?
Are you talking about the idea where they believe that we come from an ultimate being and we just live inside a giant, like...
No, I'm okay with that. That's just part of their narrative. But there was a specific saying that one of them said in the documentary, the flat earther. Can you pick that up?
Was it the lady?
No, it was the guy. It was the man.
Was it when he used heat as an explanation for the?
That was his justification that's his rationalization of the data, right? But he mentioned the Bible. Anybody pick that up?
Yeah, he was like, I can't.
I can't go against the Bible because the Bible says it's flat. And I'm like, the Bible does not say it's flat. But he was like, I will ignore the data because I believe this other, piece of information. And I was like, wow, you'll ignore science. So how do we balance science and the word? The word does not say it's flat. It's very clear that it's round in Scripture. But anyway, that was an interesting.
But then he said, well, I can't confirm that God did it this way.
Yeah.
It's like, did
Huh.
you just hear yourself?
I love the fact that if you're on a spinning earth, why aren't we flying up? And I love that when you drop a ball, it falls, it doesn't go up. And if it were spinning, it would go up. You're just like all these things like, have you ever heard of this thing called gravity? It was just crazy.
I have a question. On his, flat map.
Yeah.
Did it have the other countries? Because I'm pretty sure the camera only showed North America, but I was like, where are the
Yeah,
other
it
ones?
does. It had it all.
Okay.
It had all the continents. But the funny one is, one of you, I've graded like 3 of yours so far because I just wanted to get it was fun listening to you articulate the scientific method. But one of you said, of the 3 I graded, I forget who it was, but you said, what experiment would I confirm? I would just get in a boat and sail and find the wall, right? And it's just like, if there's this wall around Earth, just go find this big wall. Kind of like, what was the movie where they're in the bubble?
Giver.
What was it with Tom Hanks? Isn't that the one with?
Oh, the Truman Show?
The Truman Show, yeah. It's just like that. Is that really what life is? Did anybody pick up on the bias from the documentary?
Nope.
What was the bias from the documentary?
I swear I wasn't imagining this, but it seemed like they were implying that the flat Earth conspiracy is somehow tied to theism.
Oh yeah.
Yeah.
Oh yes. Yeah.
It was never explicitly stated.
No,
but
and that's why I said when
Yeah.
the guy says, well, we believe the Bible says it's flat, therefore it's flat. And of course, that's the theistic bent that they want to jab.
Yeah.
But did anybody find the bias in the documentary?
Lots of the things they brought up almost implied that flat Earth was dangerous.
Yep.
Like that.
Yeah. Dangerous, conspiracy. This is anti-society. This is anti-government, right?
They kept saying it would bring about a dark age from here that they've gone out.
Yeah, bringing a dark age, a new era of dark, we're just trusting in our own beliefs and not science. The bias in the documentary, no one picked it up. The commentators were not unbiased. The lady and the man that did the documentary for National Geographic, they were definitely pro Earth being round, anti-flat earthers. So they brought their bias into the documentary. Now, as a good journalist, you shouldn't have done that. A good journalist would have said, we've got two competing narratives. Which one of these does the data support? So if they would have been fair to being a good journalist, they also would have showed an experiment to confirm the flat Earth, if the flat earthers had an experiment, right? But they didn't even go for that. They only showed one experiment. And that experiment was good because it did confirm one over the other. It was a way of falsifying, which is what we use in science, one over the other. They did a good job of that. Real simple on a lake. I would have been in that raft though. It was like a $4 raft. You got 3 guys in it and a motor stuck there. I'm like, holy moly, no life jacket to it. That thing popped, you're dead. But they did that, at least that experiment, right? It's pretty interesting. I was invited several years ago to debate Eugenie Scott on NBC. She's the national director for the high school scientific curriculum. Quite a title. And when I got on the set, it was really nice. We're backstage and we're getting ready to go on. The commentator's name was Pete Wilson, and he was a super nice guy, super cordial. Talking, and we're just having a kind of an interesting hangout, just kind of getting to know each other. We get on set, the red light comes on, cameras are on, all of a sudden he just goes, bam! We've already proved once and for all that this place evolved, wasn't created. It's like that. Boom, I was just kind of like, whoa, there's a bias to this interview. He's not being neutral. We should have said, because you got Eugenie on one side, you got me on the other side, and it's like, wait a minute, and he's on her side. So it's kind of like, well, I guess it's 2 against 1. Okay, let's go. What do we do with that? And that's what I find interesting on a true journalism should have been equal, should have been not biased, and just said, show us why this is, and that's why the hour and 20-minute documentary does a much better job. Because it does actually go into some of the experiments that they apparently, and they're horrible experiments, but that's why it's a fun documentary to watch, because then you really get to see the scientific method just brutalized. But anyway, all that to say, I think there's one experiment that really is really simple to do. And I asked several of you, and I've read them all, so I've read 3. What experiment would you do to confirm one or the other? And I do think there's one anomaly that just absolutely decimates their theory. And that is when their little theory has the moon and the earth, or the sun, doing this perfect little dance. Okay? They're never not 180 degrees from one another. So what can't you explain by that? An eclipse. There's no way you can explain an eclipse. How is it if you're always doing this, is there some time where that moon dips under the sun? Okay? And in fact, in the longer documentary, they actually asked, one of the other scientists asked the flat earther, and the guy kind of goes, yeah, we don't have a really good answer for that one. You're like, you don't? Right?
So how do you explain sunrise and sunset?
Sunrise and sunset.
Seasons.
Well, and the thing is, and here's the other thing that they make this, so the flat earthers make this hard line, right? They do this, and they say, here's the sun and here's the moon, but that doesn't do that. The sun actually does, it shines like that. It doesn't have this hard line like they kept doing. It was also like it was computer generated. And so you're always going to have a little bit of light if it's up over there and it's truly flat. You're always going to still be able to see the sun. So it just makes very little sense.
I want to know how they explain Eratosthenes, how he literally all he did 2,000 years ago, stick a pole straight up in the sand, see where the shadow is, then send someone 1,000 miles the other way and see exactly where it is. It's like, oh, I can just use basic algebra to figure this out.
Yeah, on its original clocks, right? The original sundial, you can watch the arc. It's ridiculously.
What about the trajectory of like ICBM? Because the whole point of them is to be able to go into the atmosphere, come down, and then drop on any tangent that they want.
But,
So if there's no atmosphere, does it just come up and then just come straight back down?
Right, well, they don't believe it. They believe those are just disappearing, and that was just to use money for the conspiracy.
So all the rockets that do that are the same.
There's no satellites. No, that's all money that's gone to the propaganda to the machine. And it's all been photoshopped. You're just like, at what point did you just say enough's enough? Did you watch that?
He was like, oh my gosh. He's like, what class is this for? I'm like, chemistry. And he was like,
It's like mind blowing, right? It's just like, are we really watching this?
I think that the Earth is like this. You see it in the sky,
Yes.
the moon is round. So what is their version of the moon? Just like
That is a great, see, that's the type of, that's the another anomaly. That's what I wanted you to say. Yeah, how do you explain the moon having its phases, right? With the new moon and the half moon and all these, where is that coming from? Well, it's actually in the digital simulation that was programmed by God. And I think that's what they would have to say. I think that's,
he had like a 4K type guy.
yeah, right. Yeah, exactly. Okay, anyway, I thought that was kind of a, again, that was for the GE component of this course. That's all we have to do, thankfully. So one exercise, I could document that we talked about the scientific method. So I have to do that for outcome one. Okay. Questions on this? I saw some, the reason why I went a little bit rogue is because I saw some blank stares on this. Are we good? Okay. Let's, last thing that we're going to talk about is branching. In types of branching, I used to really dig down deep on this, but I realized that it's not necessary. It just kind of gets everyone confused, so I'm not going to do it this year. But I do want to talk about one branch. When you have propane, okay? Propane, notice this is really an important thing. Propane has two places that it can branch. It actually has three, but two of them are the same. It can branch here or here, that's the same, or it can branch here. See that? They're different. And when we get into types of carbons, this is a primary carbon, secondary carbon, primary carbon. Okay? So if it branches at the blue, it's just like what we've been calling it, the propyl group. Propyl. Because my branch has three. If I branch on that central carbon, it's a secondary carbon, it's different than a primary carbon on the outside, so it is an iso, meaning symmetrical. That's what iso means. Isopropyl. Now, those who are taking notes and engaging, listen to this. This is the only exception in the alphabetical world. It's not the only. It's the only one we will experience. I is considered part of propyl. So it's no longer propyl, it is isopropyl. That's different than dibutyl, dimethyl. That's a description of how many methyls I have. This now becomes a new, literally a new branch. So we alphabetize this off the I, not the P. Okay, that is an exception. All right, so just know that, because that's one of those little nuances. If you don't know, you might get dinged in Achieve or something. Achieve will be up this afternoon, so be able to work on it over the weekend. Okay? Are we clear on that? So if I came over here and I named this thing, and I put something that looked like that, notice that cyclopropane now has two branches coming off of it. It has a propyl group and an isopropyl group, okay? So this is going to be an isopropyl group. And just for the record, this is going to be 1, 2, because of the Continental Prelog rules, but I don't care that you know that. I will not test you on that, so don't worry about that. I just want it to be correct in your notes. So that's going to be a 1 isopropyl propyl 2 propyl propane. That's a lot of pros, okay? So I comes before P, so isopropyl propyl propane. 1 isopropyl, 2 propyl propane. Yes?
Why does that not say cyclopropane?
What's that?
Why does that not say cyclopropane?
It should say cyclopropane. Thank you. Okay, good, thank you. Yes?
So because of that functional group, is that why ethanol becomes isopropyl?
Ah, ethanol does it, but watch this. Here's propanol, which we'll get to.
Okay.
Propyl alcohol. Here is rubbing alcohol, isopropyl alcohol. They're different. The hydroxyl group's out on the end, on the primary carbon, whereas the hydroxyl's on the middle one. When we get to alcohols, we'll get there. Yeah, isn't that cool?
Yeah.
Yeah, so you're starting to see, hey, I've heard that word, isopropyl alcohol. Yeah, rubbing alcohol, okay? And if you wanted to have some fun, and we want to just throw one more propyl in, do that, you know. Be kind of cool. And that one, yeah, that one actually would give it, this one would have priority, so it would go this way. Now, again, you don't even know why. But it would be this one, this one, this one. So that would be, it's alphabetical, the cycle count, so it's going to be 1 cyclopropyl, 2 isopropyl, 3 propyl cyclopropane. Well, you have 4 propyls in that, that's cool. Okay. Okay, that's enough fun for that, right? Let's get into the next functional group, and that is the alkene. So, back to, yes?
How do you know, like, for, like, the pecking order, which one comes first? Like, how do you know first thing on that one?
Okay. I didn't want to do this, but it's called the Continental Prelog rules. So, and here's the way it works. I'll just explain it to you real quick. You don't have to put your pens down. Do not write this down, because I don't want you going back to your room and getting confused and getting frustrated, because this is not the scope of this class. Okay, so I look at this carbon. It's all about molecular weight in the first place of difference. That's the whole, these rules. Molecular weight in first place of difference. Because these are all carbons, they're all equal. So I have to go out and ask what's it connected to. So this carbon is connected to a carbon, hydrogen, hydrogen. This carbon is connected to a carbon, a hydrogen. So when you look at this, what's the first place of difference? Carbon's the same, hydrogen and carbon are different. Which one's bigger? Carbon's bigger, therefore that one usurps that one or trumps that one. Okay? And that's the Continental Prelog rules. And they're massive. They build. And again, if you're taking sophomore level organic, we have to know that. Because my chemistry majors have to know that. Okay? But not you. Because I'm not going to give you this again. This is the survey of organic, right? We're not digging down. So I won't give you a problem where that's not easy to resolve. Okay? Because again, this is not a class of nomenclature. And you're wondering what a cyclopropane has a higher one, right? You see the wheels turning there. Okay, let's move on in to alkenes. Alkenes. These are, up to this point, we've only had 2 functional groups. This is our second functional group. Alkanes and alkenes. And on Monday, alkynes and aromatics. So we're kind of building again on this whole idea. So back at the ranch, or back in chapter 4, we talked about these things called energy levels. We talked about energy levels. In carbon, it was a 1s2, 2s2, 2p2, energy level. Now watch what happens with carbon. Carbon has a really unique, in its ground state, that looks like this. If you go back and look at chapter 4, what we did to get an alkane was we said, okay, what happens since I'm at the n equals 2 quantum shell? What happens if all 4 of these orbitals mix equally, so I have an spp, I get an sp3, I get an alkane. But carbon, and it doesn't have a brain, but carbon can also do a different way of hybridizing. It can say, what would happen if I left out one of the p orbitals? What if I just leave this one out? And I mix this one, and this one. So if it does that, notice what it mixes to. It mixes to an SPP or an SP2. That's different than an SP3. And so this leaves the 2p unhybridized, and it hybridizes an S and a P and a P. So what happens with this is carbon comes in and says, I'm going to make 3 single bonds. 1, 2, 3. What would the geometry of 3 be? Trigonal, planar. Okay? So carbon can say, oh, well, that's kind of interesting. I'll go ahead and take a carbon with another carbon, but I'll put a hydrogen up here and a hydrogen up here. I'll put a hydrogen up here and a hydrogen up here. But carbon now says, okay, I'm happy that I have 1, 2, 3, but I still have this unhybridized p orbital up here. And this carbon says, I do too. Hey, why don't we let our 2p electrons rejoice together? And they form a double bond. Okay? And it comes from that right there. So it's called an alkene. An alkene. Alkane, alkene. So this happens to be ethene. And if I had something that looked like this, that would be propene. And if I had something that looked like this, it would be 1-butene. Sort of. Actually be butene 1-ene. We're not going to do that. Okay? Because this comes at carbon 1, 2, 3, 4, that tells me that that is located at 1, implying that it has to be going to 2. I don't need to say 1, 2. I know it's at 2. If it's at 1, it goes to 2. If it's at 2, it goes to 3. Okay? Now, one of the very most important aspects of the alkene is the fact that you don't have rotation. You don't have free rotation. I don't know if you remember, but when we were talking about alkanes, you had rotation. These things could spin. But here is the important thing with the alkene, one of the crazy cool things with the alkene. I'll go here. The alkene, this is what we call a molecular model of it. It actually, if you think about it, those 2 electrons from the 2p of this one and the 2p of this one, 2 electrons are found in 2 different lobes. All right, and we won't get into molecular orbital theory because it's super cool, but I save that for advanced organic. Those 2 electrons sit either here or here, and they actually never cross. It's called a nodal plane, which is bizarre. It makes no sense to us. Quantum mechanics, quantum theory makes no sense. If I'm going to go from here to my office, I walk. I'm analog. If the electron's going to go from here to my office, it disappears here and reappears in my office. Bizarre. So it's either here, not here, it appears here, and over time, it's in both places, but it never is here. Weird. So with that, what happens to this is this alkene gets fused. I can't rotate it. It's locked. You see that? That's locked. I can't just rotate it. I actually have to break up the orbitals in order to get that thing to rotate. Does that make sense? It's locked. So that said, here's what we're going to leave off with, and then we'll pick this back up on Monday. But stay with me. Don't disengage yet. This alkene is different. This alkene here is different than this alkene. here's the way I want you to view this. Again, I have a model of it, and I'll pick this back up on Monday, but you can still engage with me because I want you to see this a couple times. If I break this bond in half, and I break this bond in half, notice these methyl groups are on the same, well, let's go through here. You can see this blue line, these methyl groups are on the same side of that line. If I go through the alkene here, they're on opposite sides of that blue line. Okay, so we got opposite trans, same cis. Okay, trans is also E, Einwagen, and cis is also Z, Zuswagen. Okay, that's we're moving away from cis and trans, and we're starting to, you'll start to see E and Z more because we should. Here's why this becomes important. We have a molecule in our body that looks like this. Okay, this molecule is a miracle molecule. Okay? This is called trans retinal. Where have you heard of the word retinal? Your eyes. This is an amazing thing. Now, and keep reminding yourself this is all by chance. It was not designed. This just happened from the cosmic mind that is. This bond right here is trans. If you see it, there's the line. Those hydrogens are on opposite sides of that blue line. This molecule goes back and forth between this form. Stay with me. We're almost done. The torture is almost over. Okay? Oh, I need one more hand. Just gypped you card. Okay, stay with me, stay with me. What form of the alkene is that? Cis. So this is cis right now. Now look, check this out. This is absolutely brilliant. Whoever came up with this, whether it was chance or Jesus. Listen to this. This is cis retinal. Okay? Cis retinal, when it has a, when trans retinal has a photon, okay, it breaks the bond and it flips to cis. And because retinal is connected to a massive enzyme, you might call those rods and cones if you've ever heard that, it triggers in the brain that it flipped. And so now the big protein says signal, and it signals. And that's how we see it. And then an enzyme says, well, cis doesn't do me good because we just killed our trans. So a big cascade of enzymes goes and rebuilds it. And then does again, fire. And that's why when you look at a real bright light and you close your eyes, you can still see a shadow of that light. It's because you've consumed all the transretinal and it takes enzymes and time to regenerate it. Wow. That chance is so powerful. It's so creative too. That nothing can create that. Amazing. I feel like when I start showing off. It's not fair. I see. It actually kind of frustrates me because I won't. No point. It's a blessing and a curse. But yeah, Is that, what is that? Make sure you're. Make sure we're all somewhat healthy. Yes. This is beautiful. This is now, this is longer. This is 5 carbons. 3, 4, 5. Yeah, pentane was 5, it's not 4. So this is if it's a branch, it's an ill. If it's a parent, it's an A. Okay? And it's just if you have both a cyclo and a branch of the same length, then the cyclo wins out. It becomes the A, and the branch becomes the ill. Okay, look that over. If you have questions, bring it up on Monday. I will love you. Okay? Awesome. Okay, you're holding office.
My grandma sent me lunch and I saw for sex corrections. I was only surprised about bringing a bunch of snacks to food. And I was like, I think that's pretty good. So now that I'm part of the I didn't actually vegan yet today because Friday took their time.
Oh, and see, you know, back in the VHS days, I don't know. I have never known.
I want to eat one, but like I cut 2 pieces of my quesadilla and I just can't. I'm about to say, wait, you're actually having a meal today with us. You can't handle this. I'm starving when I go to work.
Yeah, I'll see if I can. I do think I have a
And my room's a mess.
I would have to find that, you know, in my own garage. Okay, you two come. Yes. Yes. Yeah.
I was unable to submit
Oh, that's fine.
but I emailed.
Good, perfect, you're perfect. As long as I have a copy, you're good. Okay, okay, awesome.
It feels good. It does, but I can't make myself want to before it happens. I just had
Okay, you guys ready to? So you, I lost your scan turn, or you?
No,
I wasn't here on Monday.
Okay, so you didn't get your test back. So listen, you.
Wasn't here Monday either.
You're fine. So just do your corrections over the weekend. You can do it on Monday.